Hey everyone, welcoming you all to the channel. And right from this video, we're gonna take the tutorials about Bitcoin, about blockchains, and everything around them. These videos are gonna be more mathematic heavy, and I would suggest you to have a very basic understanding of Python. That's it. So one of the most important and difficult thing about learning how to program a blockchain or Bitcoin is knowing where to start. There are so many components that depend on each other that learning one thing may lead you to have to learn another, which in turn may lead you to need to learn something else before you can understand the original thing. So this video is going to get you off to more manageable start. It may seem very strange, and surprising, but we'll start with the basics of maths that you need to understand the elliptic curve cryptography. Then later that in turn will give you the signing and the verification algorithms. There are, these will be at the heart of how actually the transactions work. And transactions are basically atomic unit of value transfer in blockchains. So by learning about finite fields, elliptic curves first, you will be able to get a very firm grasp about the concept that you will need to progress very logically. See, I just want to make you aware about the things that this video and the coming videos, these might feel very overwhelming to you, specifically if you haven't done some formal math in a very long time. So we would encourage you that you go through them, you make the concepts and the code, because these concepts and code that we'll be talking about will be used in the later phase of the videos as well, right? So what are we going to do first is we're going to talk about some higher level mathematics, right? Because see, learning about new mathematical structure, it can be a bit tough, intimidating, and this video I hope to help you out with that, with a particular thing, which is high level maths. So finite fields in particular, these don't require all that much more, say like algebra. See, think about finite fields as something that you could have learned instead of trigonometry. Except at the education system, you're part of decided trigonometry was more important. This is, my view. Okay, that algebra is really important. So this video, I just want you to, this video is going to be important because this would be very helpful when you are understanding elliptic curve, right? So let's simply get started with the finite fields first. Okay, so mathematically, if we talk mathematically about it, okay, what are finite fields actually? So these are defined as finite set of numbers and two operations, right? So we have a finite set of numbers, number one point, and the second point is we have operations. There's our addition and subtraction. Okay, and these are going to satisfy some sort of values, right? And let me just also write those. These are gonna have some sort of properties that they will always be following. We'll talk about the properties as well, right? You won't miss any of the things. These can be your notes as well. So number one, if let's say we have a and b, right, these are in the set. Okay, if a and b are in set, right, then a plus b and a dot b are also in set, right? And what we call this property, this property is called being closed. Okay, these are some of the mathematical things. I would say definitely you need to make some sort of notes, and so that these will help you in a better understanding of everything. Okay, zero exists and it has certain property, that is, if I have a and I add a 0 to it, it will always give me a. What do we call this? We call this additive identity. Additive identity. Okay, number three is going to be one has, one also exists, one also exists, and it has certain property, which is a dot 1 is always equal to a, right? Which means it is a multiplicative identity. Multiplicative identity, right? Number four, if a is in a set, right, if we have a and minus a is in the set, which is defined as the value that makes a plus minus a. If I would go this way, it would give me 0. This is what we are known as additive inverse. Additive inverse, right? Number 5 is gonna be if a is in the set and is not 0, it's a, but a is not equivalent to 0, right? And we also have a to the power minus 1 in the set. No, we have all these things in the set. So what we can say is a dot a to the power minus 1 is going to be equal to 1. What is this? This is known as multiplicative inverse. Inverse, right? So these are the very basic properties that you need to know about finite field definition. Okay, let's unpack each of these criteria. Okay, so we have a set of numbers that is finite. Because the set is finite, we can designate a number p, which is how big the set actually is, and this is what we call as the order of set. You know, this was the second thing that we talked about, that was order of set. Did you get the point? Order of set. Okay, so says that we are closed under addition and multiplication, and this particular one particularly says that we are closed under addition and multiplication. This means that we have to define addition and multiplication in a way that ensures the result stay in the set. For example, a set containing 0 1 2 is not closed under the addition, since 1 plus 2 is going to be 3, and 3 is not in the set either. Did you get the point? Let's say I have a set 0 comma 1 comma 2, and I take the value as 1 plus 2 is going to be 3, but I cannot find this 3 in this particular set. What does this mean? This means that it is not a closed set, right? So of course we can define addition a little differently to make this work, but using normal addition, this set is not at all closed. See, on the other hand, the set minus 1 0, if I take minus 1 0 and 1, right, it's closed under normal multiplication. So any two numbers can be multiplied. There are 9 such combinations, and the result is always in the set. The other option we have in mathematics is to define multiplication in a particular way to make these sets closed. We will get to know how exactly we do it. Okay, number 2 and number 3 that mean that we have additive and multiplicative identities. That means 0 and 1 are in the set. Number 4 means that we have an additive inverse. That is, if a is in the set minus a is in the set. Using the additive inverse, we can define subtraction. If the number 5, what we can say is that multiplication has the same property. If a is in the set, a to the power minus 1 in the set, then a dot a to the power minus 1 is always equal to 0, right? So using multiplicative inverse, we can define division. This will be the trickiest thing to define in a finite field. Okay, let's talk about defining the finite sets. Okay, this is the second thing. Finite sets, cool. So if the order of the set is p, if the order of the set is p, where's the blue pen? If the order of the set is p, right, we call the elements of the sets. So what will be the elements? What can be the elements? So elements can be 0 comma 1 comma 2 dot 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 and up to p minus 1, let's say, right? So these are the numbers, are what are called the elements of the set, not necessarily the traditional numbers 0 1 2 3 etc. They behave in many ways like traditional number, but have some difference in how we add, subtract, multiply, and many more things, right? See, in the mathematical notation, the finite set now would look like finite set with order p is equal to 0 1 2 dot 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 p minus 1. This is what do you call, let me just change this one. This wasn't looking really good. 1 and 2, right? This is what we will call it. So what's the finite field? What's in the finite field set are the elements. If p is a specific finite field called the field of p or field of, okay, and whatever the size of it is, that's what we call as order. Now the numbers between this particular brackets, these represent what elements are in the field. Now we name the elements 0 1 2 etc because these are very convenient right now. Okay, So if you were to there will be some sort of things that we'll be doing later, that is coding down how we would construct a finite field in the Python, right? I'll do it, we'll code it later. Okay. Then the point is modulo arithmetic. We'll now talk about modulo arithmetic. Modulo arithmetic, right? What actually is this? Okay, see, one of the tools we can use to make finite fields closed under addition, subtraction, multiplication, and division is something called modulo arithmetic, right? So we can define addition on the finite set using modulo arithmetic, which is something you probably learned when you first start division, right? So if I would give you a problem like 3 7 and 2 are 1, right? Some kind of this, these are the very basic problems. Now whenever the division wasn't even, right, there was something called the remainder, right? So let's say I take 3 to the 6 and then remainder I got as 1, right? Getting? So remainder is which is the amount left over the actual division. Now we define modulo in the same way, but we use a operator called modulo, which looks like this, right? So if I would say 7 modulo 3, what I get? I get the remainder value, that's the 1. Another example can be, if I have 7 and I have 29, right? 7 4 is 28, remainder is 1 again, right? So formally speaking, modulo operation is the remainder after the division of one number by another. Let's take another example with a larger number. Let's say if I would take 1747 modulo 250, I don't know, but there would definitely be a remainder, right? But if you have to take it into a more intuitive manner, like how would we go? So how would we do is, let's say we have a clock, okay, and it is currently at 3 o'clock, okay. What will be the time if I go 47 hours from now? Okay, so the answer would be, I'll simply go and I'll do 3 plus 47, and I'll just go with having a modulo of 12, because we have 12 hours in a day. Oh, sorry, 12 hours at a single time, and I'll get a value 2. How do we do it? Let me tell you, right? How. See, this is our clock, okay. If I'm right now at 3, and I'll have to cover this for 12 digits, right? Because I have 12 digits over here, right? So I'll be covering this for 12 digits, and I want after 47 hours, so 3 plus 47, and I'll be doing there will be the 12 times the hours will be changing in one particular rotation. That's how I got the value 2. So this will be going there, then whatever be the case, and then it will stop at 2, right? So this is how we do it, okay. So we can also see this as a wrapping around, in the sense that we go past 0 every time we move the head of 12 hours. So let's say you can do is, if it's 3 o'clock, what's are gonna be it at 16 hours ago? It was. So we'll have a very negative modulo. So a negative modulo is also possible, because let's say it's 3 o'clock right now. What will be the time 47 hours before from now, right? Or 47 hours ago, what would be the time? 16 hours ago, what would be the time? 15 minutes ago, what would be the time, right? So these are certain kind of things that you can solve with it. And in Python it's really simple. How would you do that in Python? You would simply write print, let's say I want to do 7 mod 3. Definitely you will get an output of 1. Crazy. It's really simple to do certain kind of things. Finite field addition and subtraction is something that we need to take a look at now, right? Okay, let me change the marker. Finite field addition and subtraction. Okay, so remember that we need to define the finite field addition such that we ensure the result is still in the set. We want to make sure that addition in a finite field is always closed. That was the hashtag number, that serves the rule number one that we talked, right? If you don't remember, you can just take a look at this. We want something to be in this particular way. We also talked about this thing, right? So the point is, we want the definite field addition in such a way that the result is still in the set. That is, we want the addition to be closed. Now we can say that we just learned modular arithmetic to make addition closed. Let's say we have a finite field of 19, right? Let's say we have a finite field of 19, f19. How would it look? 0 1 dot 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 up to 18, right? So now if I would take any of the number a and b, these should belong to f19, right? uh, this this symbol basically means is an element of, right? A and b is element of f19, right? So in our case, a and b elements are now, a and b are going to be the elements of f19. So addition being closed means, when I talk about addition being closed, what would that actually mean? It would mean I'm going to do an a plus b, and these are belonging to f19, right? So I'll add f over here. That means finite. So we denote finite field addition with plus f to avoid confusion with the normal integer addition. So if you utilize the modular arithmetic, we can guarantee this to be the case. So we can define a plus fb. So when you talk about modular things and finite fields, we can say that a plus finite of b is gonna be a plus b, whatever will be the a plus b, and I'll just take a modulo of this 19, or the order. And what I can see over here is that we utilize modular arithmetic and we are trying to get into the case. Now each and every answer that I'm gonna get is always gonna be less than this 19 value, and it's always gonna be a part of this finite set, right? For example, if I would take let's say 7 plus finite 8, okay? If I take this particular thing as an example right now, what would the answer be? I'll do like 7 plus 8 modulo 19. The answer would be 15, and 15 is a part of f19, and you can take any two values and you would always get an answer within this finite set, right? So we take any two numbers in the set, we add them and wrap around the end to get the sum, and we are creating our own addition operator here, but the result is bit unintuitive. After all, 11 plus f17 is 9, right? And it just doesn't look right because we are not used to finite field addition. See, 7 plus 8 gave me an answer 15 here, right? But if I would go with and say, as I just said, right, if I would go with 11 plus f of 17, I would get an answer that will be 11 plus 17 mod 19, which is equivalent to 9, right? But this is not really looking right, because you are not aware of, or you are not very used to finite field addition. So more generally, we define a plus finite b is equal to a plus b mod with the order, right, where a and b belongs to f of b. We also define additive inverse in a similar way. If you will have to talk about additive inverse, the pages are over. I'll have to change the page now, okay? But if we'll have to go with additive inverse, and it implies the same, c minus fa is equal to minus a mod of p. This is what I will call as additive inverse. I hope you got this point. These weren't really that tough, honestly. I'll add a page. I got the page now. Again, for clarity, if we use minus f to distinguish field subtraction and negation from the integer subtraction and negation. So if we had this f19, and I'll go like f9, not this one, I'll erase it, I'll take the blue pen, okay, minus f 9. So it's gonna give me a 9 modulo with 19. It's gonna give me a value of 10, which means that 9 plus f of 10 is going to be equivalent to 0, and it turns out to be very true. Similarly, we can do the field of subtraction. So for the subtraction, how would it would look? A minus infinite b is equal to a minus b, and same way mod p, right? It's okay, where a and b always will belong to fp, right? You can create your own problems and you can solve them. Okay, nothing really tough. Next is finite field multiplication and exponential. We also need to, when we have talked about addition and subtraction, we also need to talk about multiplication. Okay, let's take the example now. Okay, so just we defined an addition for finite field that was closed. We can also define new method multiplication for finite fields that are very closed, right? So by multiplying the same numbers many times, we also define exponentiation, and in this particular thing we'll go through exactly how we do this by using it, right? So multiplication is adding multiple times, right? For example, we have 5 3 ja 15, right? 5 times 3 is 15, which can be written as 5 plus 5 plus 5, right? It means we are trying to add multiple times. If I'll go with 11 into 5, I'll be like 11 into 11 plus 11 dot 11. These will be 5 times, it's going to be 55. So now we can define multiplication or a finite field on the same way, but operating in F19 one again, right? So let's try to do it. Now how would it look if we talk about the finite fields, right? It's going to be 5 dot f of 3 is going to be 5 plus f5 plus f5, right? Finite of 5, finite of 5, finite of 5, right? That's how it's going to look. Okay, and so we already know how to do the right side, and yet the yields a number in the F19 set. So 5 dot f3 will be equivalent to 5 plus f5, which is equivalent to 15 modulo of 19, is gonna give me the value of 15, exactly that way. Now note that, this was pretty simple, but what if I change some sort of values, right? This was pretty simple to understand, but let's say if I change the value, let's say if I would do it in such a way, 8 plus f of 8 plus f of 8, and it's going to be 17 times, right? It's an, there's a this 17 times, and then this would be equivalent to 8 dot 17. Then I'll take a modulo of with a 90, right? And I get something like it 56 136 mod 19, right? And with 19 it comes to 133. This is 3 that I got. So in this particular case, if you take a very closer look into it, what you would find is this result is very unintuitive. We don't normally think of 8.17 is 3, but that's the part of what's necessary in order to define multiplication to be closed, and that is the result of multiplication is always in the set 0 1 to p minus 1. Now exponentiation is very simply multiplying a number many times, right? So in a finite field we can do exponentiation using the modular arithmetic, but do we really need it? Let's try to say, if I to take a exponentiation, so if I would 7 3 ja 7 to the power 3, then it would be f7 dot f7, and if you would solve in a similar way you would get a totally different answer, right? And if you would go to 7 to the power 3, and that is 343 mod 19, this one, this is what you get, right? So exponentiation again gives a very counterintuitive results. We don't normally think that 7 to the power 3 is going to be ever 1, okay? Or 9, let's say, and again, finite fields have to be defined so that the operations always result in a number within the field, okay? So these are some sort of things that we can talk about more. And then we have the finite field division. Okay, when we have talked about multiplication, now let's also talk about the division part. Finite field division, right? Cool. Okay, let's get with it. So now the intuition that helps us with addition, subtraction, and multiplication that we've already done, and perhaps the even exponentiation. It, unfortunately doesn't help us quite as much with the division. See, because division honestly is the hardest operation to make sense of. We'll start with something that should make really a sense, and then we'll go to something that don't make sense, that is very intuitive, you know. So if we have 7.8, it is 56, right? And in similar way, if I will divide by 7, it will give me a value 8. Or if I would have done it with 56 divided by 8, I would have gotten a value 7, right? Let's say if we have 12.2 is equal to 24, and vice versa. If I would go 24 by 12, I'll get a 2. Or if I'll go with 24 by 2, I'll get a similar 12, right? And so on, for every case that you take, this is the something that's going to happen. Now, we use this as a definition of division to help us. Note that like in normal math, you cannot divide by 0. In F19 case, we know how it's gonna work. So let's see, in the finite field case, 3 dot f7, let's say it would imply 21 mod 19. It will give me a value of 2, which will imply that 2 divided by 7 is 3, right? And 9 dot f5, let's take another example, 45 mod 19, which is equivalent to 7, and it would definitely imply what it would imply is 7. If I would take f5, it should give me 9, right? This is something, but don't you really think it's very absurd? It's very intuitive. Yes, as we generally think 2 f7 or f f by f by f 7 by f5 as fractions, not nice finite field element. Yet that is one of the remarkable thing about the finite fields. Finite fields are basically very closed under the division. That is, dividing any two number where the denominator is not 0 will result in another finite field element. The question you might be asking yourself is, how do I calculate 2 by f7? And if you don't really know beforehand that 3 dot f7 is equal to 2. Now this is very indeed an amazing question, right? To answer it, we'll have to use the result that we have already seen. So in case you didn't get it, the answer is that n to the power p minus 1 is always 1 for every p that is prime. And n should always be greater than 0. Now this is a very beautiful result, if you take a look at it, because from the number theory called Fermat's little theorem, and specifically this theorem actually says is Fermat's theorem actually say, we're taking a deep turn into this, right? N to the power p minus 1 modulo of p is always 1, where p is going to be prime. Okay, let me just say p belongs to prime number, right? Since we are operating in prime fields, this will always be very true. Okay, there can be a lot of proofs for the Fermat's theorem, but I don't really think so that is really required at this point for this particular video. We are not into mathematics class all the way, but yeah, we are just trying to get a hold on what actually the mathematical values hold over here, right? See, because now division is the inverse of multiplication, we know that if we go with certain things like a divided by b is going to be a dot f of 1 by b. It's not gonna be always a dot f b to the power minus 1. So we can reduce the division problem to multiplication problem as long as we know we can figure out what b to the power minus 1 is. And this is exactly where Fermat's little theorem comes into the play. Now we know that b to the power p minus 1 is gonna be equal to 0 when p is prime. So b to the power minus 1 is equal to b to the power minus 1 dot of f1, and b to the power is equivalent to b to the power minus 1 dot f b to the power p minus 1 is equivalent to p minus 2. And keeping it really more simple, I could have simply said b to the power minus 1 is equal to b to the power p minus 2. So in F19, this means practically that b to the power 18 will be equivalent to 1, which means that b to the power minus 1 will be equivalent to b to the power 17 for all the values for p greater than 0. If you don't, let me just write it down again. If we have F19, it was the finite set of 19 order, right? It would practically mean that if I would take the value of b to the power 18, it's gonna be 1, which means that b to the power minus 1, which will imply u, right, will be equivalent to b to the power 17. Are you getting the point? This is what this picture is all about. Okay. So in other words, we can calculate the inverse using the exponential operators. So it's a relatively very expensive calculation, as exponentiating grows very fast. Now division is the most expensive operation for that reason. To lessen the expense, we can use the pow function in the Python, which does exponentiation. Now in Python, pow, when you actually wrote pow 7,17, right, it does the same thing as 7 into 17. Now the pow function, however, has a very optional third argument that makes our calculation very more efficient. Specifically, pow will modulo by the third argument. Thus pow, you went, so it will be like pow 7, 17, 19. This will give us the same results as 7 multiplying by 17 and then modulating with 90, but it do so faster because the modulo function is done after each round of multiplication. That is why we use pow rather than multiplying all these stuffs. These are just mathematical stuff, and this is pretty much the conclusion for this particular tutorial, because we have learned about finite fields, and we will also learn about how to implement them in Python in the next video, right? So stay tuned for the coming of the videos, and I can pretty sense that this might have been a quite intimidating thing for you. These really weren't that simple, but you will have to put in your time, you'll have to put in your understanding, your intellect, and make sure you follow the tutorials really well, and we'll have many more such videos coming up. Okay, have an amazing time, be healthy,